What causes the pitch of a sound to apparently increase as it moves toward an observer? Likewise, why does the pitch of a sound apparently decrease when the object moves away? This is what is known as the Doppler Effect. The frequency of a sound refers to the number of sound waves per second, and this gives sound its pitch. A sound with a higher pitch has higher frequency, and a sound with a lower pitch has a lower frequency. The general relationship between the frequency you observe and the frequency emitted is characterized as follows. The frequency of the observed sound is equal to that of the sound emitted, multiplied by the velocity of the sound plus or minus the velocity of the observer over the velocity of the sound plus or minus the velocity of the source of the sound. We can break this into different components from different scenarios. Let's consider, for example, a truck coming at you full speed blasting music. The truck emits sound waves, and as it approaches you, each sound wave is emitted from a position that's closer to you than the wave before, so each wave hits you faster than the one before it. Since the time intervals between each wave arrival reduces with each wave crest, this means that you're detecting more waves per second, so you hear a higher frequency, which means a shorter wavelength. The shorter wavelength perceived by the observer is given by the following. The distance the source of the sound has moved is subtracted from the distance traveled by the wave. The wave distance is equal to its wavelength, and the source distance is equal to the velocity of the source multiplied by the time between emissions of wave crests. The time interval can be rewritten as wavelength over the speed of the sound. Therefore, we can rewrite this as shown. From this, we can derive the change in frequency. So, this scenario of a source of sound moving towards a stationary observer can be described with this relationship. Notice that the denominator will be less than 1. This results in an observed frequency that is higher than the emitted frequency. Now let's imagine the truck drives past and away from you. Each wave takes a longer and longer time to hit you because the waves emitted from the truck are coming from a point farther and farther away each time. Therefore, you are going to perceive a lower pitch because you're receiving less waves per second, which is a lower frequency. In this scenario, the relationship is similar to the previous equation, but it has a plus sign instead of a minus. Therefore, the denominator will be greater than 1, and the observed frequency will be lower than the actual one emitted. The reverse also holds true. Let's say you're traveling toward a stationary truck that's blasting music. You'll hear a higher pitch, and if you're moving away from a stationary source emitting music, you'll hear a lower pitch. In these scenarios, the wavelength, or the distance between the wave crests, stays the same, but the velocity of the crests with respect to you, the moving observer, changes. The scenario of an observer moving towards a stationary source is described by the following. Note that there's a plus sign, so the ratio of the velocity of the observer to the velocity of the sound is being added to 1, which, when multiplied by the emitted frequency, results in a higher detected frequency. In the opposite scenario, when the source is stationary and the observer is moving away, a minus sign is used, which results in a lower observed frequency. This explains why this general equation can be used to combine any number of combinations with moving and stationary sources and observers, and it helps explain the weird auditory illusion of the Doppler effect.